Hello friends, welcome to my channel again, and today we will discuss Cement Grouted Bituminous Mix or CGBM. Now this mix comes under the category of semi-flexible material or semi-rigid material, and therefore it has advantage of both flexible pavement as well as rigid pavement. As you all know, flexible pavements are the most common types of pavement used for highways not only in India but in other parts of the world also, and the bituminous wearing cores of flexible pavement generally suffer wet weather damage, which is more common in cities due to flooding during monsoon. Similarly, pavements at traffic junctions, parking places, and bus stops are damaged due to frequent braking and fuel spillage. Therefore, wearing cores at such locations should be such that it is strong enough to resist the braking and acceleration effect of traffic. It is fuel resistant and it is impervious to water and resistant to moisture induced damage. And fortunately, this cement grouted bituminous macadam satisfy all these requirements of a wearing course. In short, the CGBM is almost a single graded bituminous mix having air wires more than 25%, and it is paved and grouted with cement grout. Now the cement grout is primarily prepared by mixing suitable proportion of cement, fine sand and water, but other materials like fly ash, microsilica, superplasticizers may also be added to improve the flowability and strength of the grout. And because wires in CGBM are filled with grout, so it has advantage of both flexible and rigid pavement. The surface is impermeable and it provides resistance to moisture induced damages. It has good resistance to permanent deformation and resistance to oil induced damages, particularly in parking areas. And it has higher flexibility than rigid pavement. There is no joints as in the case of rigid pavements, and high static bearing capacity and distribution of stresses take place in case of CGBM. Lower thermal susceptibility, it provides good skid resistance and quick constructability and opening to traffic. Now there are several countries in the world where this material has been used, like UK, France, Denmark, Saudi Arabia, Great Britain, South Africa, Sweden, China, Japan, and many more countries. This mix has been laid on a few experimental trials in India also, and based on their performance, IRC has brought out a code IRC SP125 on design and application procedure for CGBM. Materials required for construction of CGBM are same as in any other bituminous layer, that is aggregate and binder. Now here we need cementitious grout also to fill the wires in the bituminous layer. The physical requirement for coarse aggregate shall be crushed rock retained on 2.36 mm sieve, and they should have the physical requirements as given in this table. The cleanliness, that is material passing 75 microns, should be less than 2%, and particle shape, strength can be either in abrasion value or in impact value. Polishing value should be more than 55, and durability is important when water absorption exceeds 2%. Fine aggregate is the material passing 2.36 mm and retained on 75 micron, and it will be 100% crushed manufactured sand resulting from stone crushing operations. It will be clean, hard, durable, of fairly cubical shape and free from soft pieces, organic or other deleterious substances. These requirements are same for all bituminous layers. The sand equivalent test value for fine aggregate should be more than 50, and plasticity index of the fraction passing 425 micron sieve should be less than or equal to 4. You can watch another video on sand equivalent test, and the link for the same is given in the description box. The bitumen can be either viscosity grade binder like VG30 or VG40 complying with IS 73, or it can be polymer modified binder of grade 40 complying with IRC SP53. The grout will consist of cement, sand, fly ash and superplasticizer. Cement can be OPC 43 or 53 grade. Sand should be passing 0.6 millimeters so that grout will enter into the air wires easily. Fine sand passing 45 micron can also be used, and that also gives a good grout. Addition of fly ash or silica fumes can increase the flowability, and superplasticizer or other chemical additives help in reducing the water requirement of grout and can help in early gain in strength. The mix design for CGBM. Initially, there are all steps which are generally used for design of a bituminous mix. The first step is to select the aggregate gradation, and that would be for open graded with dominance of single size aggregate to create 25 to 35% air wires in the mix. The combined grading of coarse aggregate and fine aggregate for CGBM are given in this table. And this CGBM can be laid in a layer thickness of 30 mm to 50 mm. Now here grading 1 and grading 2 are same as given in MOR test specification for surface tracing. Grading 3 is taken from ASTM for open grade friction course. And this will have slightly less air wires than the first two gradings. Selection of any gradation for CGBM can be made with the objective that grout flows freely in the air wires. And the gradation has effect on the packing of aggregates, and that affects the air wires. And this packing characteristics can be defined in terms of dry aggregate air wires. The procedure is given in ASTM C29 to determine the air wires in dry loaded condition. Now this method is to determine the bulk density of aggregate in a specified compacted condition. And for this, a cylindrical measure of 10 liter capacity is taken, and its volume is determined by filling it with the water. Then use dry loaded procedure to place and compact the oven dry aggregate in the measure. Fill the measure up to 1/3 depth and then compact it with 25 blows of tamping rod evenly distributed over the surface, and then you put another layer of 1/3 depth and again give 25 strokes of tamping rod, and finally the third layer which should be overflowing, and then you remove the extra aggregate after compacting it with the 25 blows of tamping rod, and then take weight of the aggregate and cylindrical measure. And that is how you determine the bulk density of aggregate. That is the weight of aggregate required to fill the cylindrical measure divided by volume of the measure. Now once you know M, then percent air wires can be estimated using this equation: 100 into S into W minus M upon S into W, where S is the bulk specific gravity of aggregate on dry basis and W is the density of water. The third step is to determine optimum binder content, and it is determined by drain down test, which is given in ASTM D6390. This method determines the amount of drain down in an uncompacted asphalt mixture sample when the sample is held at elevated temperature, which is encountered during production and transportation of the mix. So what you need is a forced oven draft which can maintain a temperature 120 to 175 degrees centigrade, plates or containers capable of withstanding oven temperature required for the test, then a standard basket which is 165 millimeter deep, 108 millimeter wide, and with a basket bottom at 25 millimeter above the bottom of the basket. Now this provides basically the space for drain down. So mixture is kept in this basket at this level, and then when the temperature goes up, then it drains down. And a balance. Now what IRC suggests that for each mixture to be tested, the drain down characteristics shall be determined at two temperatures. One at the anticipated plant production temperature, and the second the temperature higher than the anticipated production temperature. and duplicate samples shall be tested at each temperature, and therefore a minimum of 4 samples will be required to be tested. Now this drain down test is like this, that first you take the empty weight of the basket, and let us say this mass is A. Then prepare the mixed sample and place 1200 grams of the hot mixture in the basket, and take the weight of the sample plus basket, let it be B. Take the weight of the plate and hang the basket with the mix in the oven, which is preheated to a selected temperature. Place the catch plate beneath the wire basket and keep the basket in the oven for 1 hour plus minus 5 minutes. After that, remove the basket and catch plate from the oven. Let it cool to ambient temperature, and then determine the mass of the catch plate plus the drained material to the nearest 0.1 gram, and let us say this weight is D. So drain down value is calculated by this equation, D minus C upon B minus A into 100, where this D minus C is the weight of the drained material, drained asphalt, and B minus A is the sample taken initially. Drain down will increase with the bitumen content, and the limiting value here is 0.3. So corresponding to 0.3% drain down, you determine what is the bitumen content required. And this is the optimum bitumen content for CGBM. But this OBC should not be taken less than 3.25%. Otherwise, it will not be possible to coat the aggregates properly. The samples for CGBM are to be prepared at higher air voids, and therefore the next step is to determine the compactive effort to get the desired air voids. And as you all know, air voids reduces with the number of blows in a Marshall specimen, and therefore IRC suggests that for gradation 1 and 2, 40 blows will be sufficient to get the air voids, and for gradation 3, 60 blows will be required, and all these blows are to be applied on one face of the Marshall specimen only. But actual number of Marshall blows are to be determined by trial and error, so that you get the desired air voids of 25-35%. And once you know that, then the next step is to prepare the sample and test them. And for that, 4 samples of the bitumen content selected as per drain down test are prepared. 3 samples at the number of blows as found out earlier, and they are used to determine the volumetric properties of Marshall specimen. And the 4th uncompacted loose mix to determine the theoretical maximum specific gravity as per ASTM D2041. And this method I have explained earlier also in another video. Now the selection of job mix gradation is based on 2 parameters: voids in mineral aggregate VMA and air voids in the mix VA, and they are calculated using these equations. VMA is 100 minus GMB into PS upon GSB, and VA is theoretical specific gravity minus bulk specific gravity divided by theoretical specific gravity. And PS here is percent of aggregate in the mixture. GMB is the bulk specific gravity of compacted mix. So based on these 2 parameters, you determine the aggregate gradation which will satisfy VMA and VA. Once you decide the optimum gradation and the bitumen content in the mix, the next step is to optimize the grout. Now, optimization of grout basically means fixing water content in the grout so that it penetrates to full depth with optimum strength. And as I told you earlier, the grout consists of cement, sand with special additives. It can be fly ash and plasticizers. There are 2 requirements of grout. One is fluidity, another is strength. The fluidity of grout is measured using flow cone as per ASTM C939, and strength is evaluated in terms of its compressive strength measured on casted grout specimen as per IS code or ASTM code. The quantity of mixing water in the grout needs to be optimized to have the optimum balance between its flow and strength parameter. And that is how the grout should penetrate to the full depth. It should not be a partial depth grouting. That is important. So if you increase the water content in the grout, its mass flow value or fluidity increases, or mass flow value in second reduces. And similarly, the compressive strength also depends upon the water content. So the design of grout basically means the optimization of these two parameters so that the fluidity and compressive strength both are achieved. The flow test is conducted using mass flow cone apparatus as given in ASTM, and what you need here is a flow cone with standard dimensions, a container here to receive the flow of the grout, a stand or other device capable of supporting the flow cone in a vertical steady position with the receiving container, and stopwatch, and a grout mix which is to be tested as per ASTM C938. So in the procedure is that moisten the inside of the flow cone by filling the cone with water, and 1 minute before introducing the grout sample, allow the water to drain from the cone. So you fill the cone with the water and remove this water just 1 minute before the introducing of the grout. Then close the outlet of the discharge tube with finger or a stopper. Then introduce the grout into the cone until the grout surface rises to contact point gauge. Start the stopwatch and simultaneously remove the finger or stopper. Stop the watch at the first break in the continuous flow of grout from the discharge tube. And average time of the efflux to nearest point 2 seconds is reported as the flow value of the grout. For satisfactory performance of CGBM in field, IRC SP 125 has given some recommendations for design of this mix. The grading, it can be either grading 1, 2 or 3 depending upon the requirement, or you can also design your own grading giving 25 to 35% air voids. The binder content as per drain down test, but minimum 3.25%. The grade of cement for grout can be either OPC 43 or 53, and if you are using fly ash, it should be tested as per IS code. The initial setting time of the grout should be 4 to 5 hours and final setting time 6 to 10 hours. The characteristic compressive strength of the grout should be 40 to 100 Newton per millimeter square, and flexural strength 5 to 7 Newton per millimeter square, and fluidity as measured as per ASTM C939 should be 20 to 50 seconds. The voids in CBM at 7 days should be around 2 to 3%. Full depth grouting should be achieved up to 97 to 100%. And after the grouting of the specimen, the compressive strength at 28 should be more than 5 Newton per millimeter square. The rigidity modulus at 28 days at 35 degrees centigrade should be more than 10,000 Newton per millimeter square. The flexural strength should be minimum 2, and Marshall stability at 28 days at 60 degrees centigrade should be minimum of 60 kilonewton. The ITS at 35 degrees centigrade after 28 days of curing should be more than 1 Newton per millimeter square, and retained ITS strength at 28 days should be at least 97%. The CGBM layer can be 30 or 40 to 50 millimeter depending upon the traffic intensity, and the site can be open to traffic after 24 hours of laying of CGBM, and skid resistance, which is measured in terms of BPN, should be more than 55. CGBM production is to be done at laboratory scale and then in the field during pavement construction. The parameters which are required to be satisfied in the laboratory are dry aggregate air voids, dry aggregate void ratio, voids in the mix, and voids in mineral aggregate. And these are the requirement of the CGBM production in the laboratory. Now, few points are to be noted here, that in laboratory scale production, dry aggregate air voids and dry aggregate void ratio, which represent packaging characteristics of dry aggregate, are related to each other. Vertical permeability and air voids are also related. The aggregate packing parameters DAAV and DAVR have good correlation with air voids in the compacted mix, vertical permeability, and voids in mineral aggregate. And the amount of grout penetration is correlated strongly with air wires content and also with vertical permeability of the mix. Various engineering properties of CGBM like Marshall stability, compressive strength, ITS, flexural strength are to be determined in the laboratory before recommending it for field production. So you need to determine the Marshall stability of Marshall specimen after grouting of the specimen and proper curing. These are the grouted bituminous mix in the split mode. And they are cylindrical specimen. You can see here the grout has gone up to the full depth. Similarly, beam specimen. This is not really a grouted material, but this is partially grouted, this is fully grouted beam. The pavement construction in field, the steps involved are that existing bituminous surface is cleaned. Then above that, emulsion or bitumen is spread over it as a tack coat. Layer of open graded hot high wired bituminous mix is then laid using the paver and compacted with a small wheeled roller as we generally do for a BM layer. Once the compacted bituminous surface cools down to ambient temperature, the requisite quantity of cementitious grout material mixed thoroughly with water is then poured and spread uniformly over bituminous surface. The grout should automatically flow into the wires due to gravity and its flowability. But sweeping and squeezing can also be adopted to accelerate the process of grout penetration. This exercise also avoids formation of thin layer of grout over the bituminous surface. The grouted surface is allowed to set for 1 day and then open to traffic. However, the section is cured by sprinkling of water, which is to be practiced for 7 days. So friends, thank you very much for watching this video. I hope you understood the basic concept of CGBM and how its mix is designed. You can write your comments in the comment box.